So first of all, what is different about number 2? There's more. There's 3 pieces instead of 2 pieces. And if you're like, does that make this problem a lot harder? The same process that we used over here works over here as well. So let's just first identify how many pieces this function is going to have. And you know what, before we get too far in this, let's go ahead and just box off these tables with the first one so that we do not get confused. So this one has 4 function pieces. Function piece number 1, let's go ahead and draw that squiggle bracket again. F of x equals 4. That's going to get a table for that function piece. And folks, I strongly recommend writing the equations above each table because otherwise it's even more confusing. So f of x equals 4, you get a table. F of x equals negative x plus 2, you get a table. And the last function piece, f of x equals 2x, you get a table too. So 3 tables that we are going to have to choose inputs for. So we can't choose whatever we want because we are restricted on inputs based on those bound statements. So let's just go ahead and draw a, I don't know, a funny shape, cloud shape, around those bound statements. From the bound statements, we get everything we need to know about filling out the tables and structuring our graph. First, bound value-wise for our bound lines. We've got a bound value at -5, so we're going to make a line at -5. Then I have another bound value at -5. So, yep, same line at -5. Just like we had 1 and 1 over here and got 1 line, we've got -5 and -5 over here for 1 line. That shows me where my function is going to stop being the maroon piece and start being the orange piece. And then I've got this guy and this guy. This means we are going to have another bound line at 0. But why? To make the problem more complicated? No, because we actually need this other breaking point to accommodate all 3 function pieces. These 2 lines have divided my graph into 1 area, a 2nd area, and a 3rd area, 1 for each function piece. So we've got our bound lines from the bound statements. Next, we use these same values to start these tables. So that first line, f of x equals 4, is defined for x values less than 5. Even though -5 is not less than -5, we still have to start our table with it. But how do we show that it's not really an included value? Open dot. So even though this function is only defined for x values less than -5, we need that -5 open dot value to show that's where it stops being that function. Moving on to our next table. This one has 2 bound values. It has -5 and 0, and the other x values it can have are sandwiched in between. We're going to write -5 first. We're going to leave space for a second number, and then we're going to have 0. This piece is sandwiched in between 2 bound lines, so I'm going to have to know what it's doing from bound line to bound line. Now, at the -5, will it be a closed dot or an open dot? It's x greater than or equal to 5, so that means it's defined there, closed dot, and x less than or equal to 0, so it's a closed dot there as well. See if you can decide on what bound value you're going to use in the last table, and will it be a closed dot or an open dot? Started with 0. That's the bound value that goes to that function piece. And is it going to be a closed dot or an open dot? Open, because it's x greater than 0. So it's not actually defined at 0, but I still need to start my table with those bound values. Any questions on where any of this stuff came from? Monday's going to come around. We're going to hit all this stuff again, so don't worry if you're like, ugh, I probably don't have questions now, but come Monday, I probably will. That's why we're going to go over it again on Monday as well. Just wanted to get the brain thinking about this stuff for over the weekend. So, folks, let's go ahead and go back to our first table, and let's start thinking about what we're going to pick for those two other points. Third block kind of blew it with this one, so I want to put it on your radar why they blew it. We want x values that are less than -5. So is it going to be -4 or -6? Don't even say it out loud. Think about in your brain what you think it is. What value is less than -5? Folks, on a number line, which direction is less than? If I say I want stuff less than 4, which way am I going to go? This way. So if I want stuff greater than, it goes to the right. Less than, it goes to the left. So if I want to pick something that's less than -5, where am I going to go? To -6 or -4? -6. And I had a lot of people who said -4, and I see it time and time again on the test. The negatives cause problems. So if it helps, you've got this happy graph right in front of you. Just look at -5 and say less than is going to the left, and that's what's going to take you to your -6. The other thing that will help you is, let's say we were doing this problem, and instead of going this way with my pink line, I was like, oh, we're going this way. What is the problem with this graph with the pink function over there? That is not going to pass the vertical line test anymore. So if you goof something with the signs, usually you're going to have an overlap of two pieces in one area. So that's a good way of checking yourself, is with that vertical line test. So -6, then -7. Moving on to our next table. We want x values between -5 and 0. So -4, -3, -2, or -1. Any of those are fine. I'm going to go with the easiest one, which I think is -1. But it doesn't matter. You can pick any of those points in between -5 and 0. On your own, see if you can decide on the other two inputs for the green line. We want x values greater than 0. What's greater than 0? 1 and 2. Lovely. That's the toughest part about these, is figuring out the table structure. From here, it's plug and chug and graphing and putting your arrows on. So let's actually start with the green one. We'll see why. I don't want to go directly to that maroon one. Let's start plugging in these inputs. 2 times 0, and for the x is 0. 2 times 1 is 2. 2 times 2 is 4. So 0, 0 with a nice big open dot for old Mrs. Cairo to see. 1, 2, irregular dot. 2, 4, another regular dot. Am I going to draw my arrow up and to the right or down and to the left? Up and to the right. It actually always follows the direction of your points, because we structured those based on the inequalities. So it's always going to go in this functions area. So there's piece number 1. Piece number 2. Hey, what happens when I take a -5? It becomes a +5. So -5 is 5. And then I add 2 to it, and 7. Hooray. -1 is 1 plus 2 is 3. -0 is 0, and then plus 2 is 2. So -5, 7 is up here. Closed dot or regular dot. -1, 3 is here. 0, 2 is here. Where are we going to draw arrows on this line? Trick question. We aren't going to have any arrows. Since this one is sandwiched in between two bound lines, that's it. It can't arrow over here because then it's in the green lines territory. Can't arrow over here because that's territory. So when we have multiple function pieces, if one is sandwiched in between two bound lines, no lines at all. This is why, folks, I'm picky about putting the arrows on your graph on all the other problems, because on these ones, where you have arrows and where you don't have arrows is significant. All right, folks, now for this maroon problem. What is a little upsetting about that equation? F of x equals 4. What's the problem? We picked all these nice, lovely inputs, and there is no x there for us to plug in for. So what are we going to do with this one? Well, f of x is the same as y, so I would recommend thinking about this as y equals 4. Whoa, throwback to Unit 1. What do we know about solo y equations? Are they this way or this way? They are horizontal. Good old Hay equation. So this is going to be a horizontal line. If you're like, okay, but that still doesn't help us with this table. We briefly talked about this early on in Unit 1. If this says y equals 4, that means that is the only thing that y can be equal to. Pick whatever you want for x, but that y value is going to be 4. So when you have something like f of x equals 4 or a constant value, you can autofill that table with 4s. And if you're still grumping like, well, then why did we spend all that time looking at those inputs? The inputs still matter. It's not about the y values. It's about where our x values are restricted for the piecewise function. So let's plot these points. Backwards 5, up 4, the open dot. Backwards 6, up 4, boink. Backwards 7, up 4, arrow going to the left. So this part of the graph, x less than -5. This part of the graph, x is between -5 and 0. And this part of the graph, x is greater than 0. Does this pass the vertical line test? We are good here. And here. And here we're only hitting that closed dot. And here, and here, and here we're only hitting the closed dot. Here, here, here. No place will a vertical line hit the graph more than once. So it passes the VLT. Check. So our piecewise function checks out as a function. The domain would be all real numbers, which is weird. We don't need to write it for this one, though. Folks, you have done amazing work. I hope you have a fabulous weekend.